recording. All right, so this is the stretched length that you will get by applying 4.9 newtons to the spring. But it won't. 4.9 newtons will not stretch it any further than that. If you want to stretch it further than that, you need more force. So to stretch it now this far, you're going to need 0.6 times 9.8 newtons, and that'll stretch it this far. Okay, so and then another thing that we want to. All right. So the relationship of force required to the distance that you stretch it is called Hooke's law. Okay, so it says that the force required to keep a spring displaced from rest is proportional to the displacement from rest. So the amount of force required is proportional to how far you stretch it. The further you stretch it, the more force is required to stretch it, to continue stretching it. This x value, this is really important, it's not the full length of the spring. X is not this. This is not x. X is the additional displacement from rest. So instead, x would be this is your x, okay? Not the full length of the spring, but just how much further you stretch it or displace it from its just normal at rest length.
Is Hooke's law just for springs, or is this going to be applied to other stuff?
For us, it's just for springs. I'm pretty sure it's just for springs. I don't know. I don't think it applies to other things. Well, I mean, it might apply to other things that, are resistant when you stretch them, but that's mostly springs. That's mostly springs.
Yeah.
All
right, thank you.
Yeah.
I have a question.
Sure.
When the resting position of the spring is not when the spring is fully compressed, does that mean x is just negative?
So no. I know what you mean. So if you're not applying any force to the spring has a natural length without applying any force to it. That would be x equals 0. Does that answer it?
Yeah, I mean, what I mean is, like, if you were to, in that particular picture, if you were to push the weight upward, and then the spring would be pushing down on the weight. So would you just consider x to be negative in that case?
No, x will always be positive. So that it's the same thing whether you pull the spring or push the spring. X will be a positive number. That's how far it's from its natural length.
Okay, that answers the question.
Yeah, so yeah, x will always be positive. Okay, so let's look at this. So what it means then, what we're talking about, means that if you stretch the string a little bit further, say delta x, okay, is 0.05, well then there'll be a change in force required. Okay, so the change in force required in this case, it's if you change the spring by 0.015 meters, there's going to be an additional 0.98 newtons required because that's comes from for this particular spring 0.1 more kilograms of mass will stretch it 0.015 meters, and that's an additional force of 0.98 newtons. So this is what, for this string, determines what the spring constant is. There's a constant of proportionality of additional force to additional stretch. Like how much additional force is needed for an additional stretch? Well, that's according to this constant of proportionality. So for this spring, that's 65.33. So for a slinky, you know what a slinky is? A toy? It's like a really super loose spring. What about the constant of proportionality for that? Super low, right? And then if you have like a shock on a car, like on your car wheel, there's shocks, there are springs that are, you know, absorbing the bumps on the road. That has a really high value of K. In order to change the displacement of those springs, it takes a big change in force. So your K is high. Okay, what do you notice about this equation? Really, we have the change in F equals K times the change in X. What does that make K? Does anyone notice what we're looking at here?
Rate of change.
Yeah, so this is like our dy equals mdx equation, right? So K, the spring constant, is a constant rate of change. Rate of change of force with respect to displacement. Okay, anybody have a question so far? All right, so how much work is required to stretch a spring? We'll say this spring. Let's say 0.2, no, that's too much, 0.15, doesn't matter, 0.14 meters. Okay, so can we use force times distance? We got a distance that we're gonna stretch the spring 0.14 meters. Can we multiply by the force and to get the work? Will it work? In stretching that spring, will it be a constant amount of force from 0 displacement to 0.414 meters displacement? No. As you stretch the spring, it continually takes more and more force to keep stretching it. That's what this shows. So we can't just do force times distance. So what do we have? What do we have to do that? We have net accumulation function, right? So we're going to find the work for this spring. And all we need is the rate of change of work, which we've learned before. What is the rate of change of work?
Force.
Force, right? Rate of change is force. And that we know that force is variable, right? So that's why we're doing a net accumulation function, because the force is going to vary as x varies from a to x. According to what? So what is our rate of change function? So force, okay, and what is the force to stretch a spring T meters?
The rate of change K times the increments in the inflection.
Yeah, force for the spring is K times X. So we can do KT dt. Right? The force depends on how far you stretch it. As you continue stretching it, the force continually has to increase to keep stretching it, according to Hooke's law, K times T. So since force is the rate of change of work, we can use that as in our net accumulation function. And we wanted to know, we wanted to stretch it 0.14 meters. So we're doing the work of 0, 0.14.
Why do you need for the rate of change, why do you need it to be K times T dt?
Because that's the force required to stretch a spring to a distance of x. That's Hooke's law. The force required is proportional to the distance that you stretch it. So as you continue to stretch a spring, it requires more and more force to keep stretching it. So force
Okay.
is a function of how far you stretched it by a constant K. Did that answer it?
Yes, that did.
Cool. So what is our K? Our K is a 65.33. So we wrote the work accumulation function, and I could put the 65.33 right there. Okay, I have it as K, but it would, for this spring, it'd be 65.33. So now I want to know W of 0, comma 0.14 using this function. And so we could also write it this way. And so let's just, so we could, for time's sake, we won't, but so basically you're going to, just like you've been doing over and over and over and over again, you're going to put in this net accumulation function with the K being 65.33. And then you simply type in your function notation, W of 0.14, and that will give you the work. That will give you the work to stretch the spring 0.14 meters. Okay, does that make sense? Any questions on that?
I have a quick question.
Sure.
So where you wrote rate of change on the left, is the rate of change the accumulation, that integral of K of t dt?
So there's two rates of change going on here. So this is the rate of change of force with respect to distance stretched. Because this is, dF equals K dx. So this is the rate of change of force with respect to displacement. But then force is the rate of change of work.
Got it.
And so because force is the rate of change of work, that's what we use in our work net accumulation function. So so it's two rates of change here going on. So the K is the rate of change of force, and then the force is the rate of change of work.
Okay, thank you so much.
Sure thing.
If K wasn't given, do you just use algebra and find K? Or
Yeah,
is it gonna usually be
and in fact, that's what we did. This is kind of what I did here. So the given here was that it took 0.98 newtons to stretch, an additional 0.98 newtons to stretch the spring an additional 0.051 meters. And that's how we solved for K. They just did it down here.
Okay.
So yes, to solve for K, you will need a force and a corresponding displacement. And that allowed you to solve for K. And then you're going to use that K in your net accumulation function for work. Any other questions? Okay, here's another. Please.
Is distance always going to be like in meter, like in SI units?
It doesn't have to be, right? So you could also have feet, and then pounds, and your spring constant could be in pounds per foot.
Okay. Thank you.
Yeah, sure. Okay, so let's look at a different question here. So, what's the work required? So here's this review. Let's just do a general form of a work function. What's the work required to stretch a spring with a stiffness K from its natural length x, from its natural length to x meters past its natural length? Okay, recall the force required to stretch a spring is F equals Kx. So I really want to write here. So how will we write the net accumulation of work to stretch a spring from, say, an A displacement to any displacement x?
It'd be integral a to x kx or kt dt.
That's it. Okay? Because the rate of change of work is force, and the force to stretch a spring that far is K times T. Okay? It takes a greater force to keep stretching the spring. Don't forget that. It takes increased force to keep stretching a spring greater and greater. That's why we need to have an integral accumulation function. As soon as you stretch it a little bit further, you're requiring more force to do that, and more force. Okay, so here's a question. It takes 50 joules of work to stretch the spring 0.08 meters past its natural length. How much additional work would it take to stretch it from 0.08 to 0.13 meters? So how are we going to do this? So let's understand what we have here. We have 50 joules of work to stretch the spring 0.08 meters past its natural length. So there's work of 50 joules is associated with x of 0.08 meters. And if I want to figure out some additional amount of work, I'm going to need a work accumulation function. And to have the work accumulation function, I'm going to need my force function, right? My force function for the spring. How am I going to get my force function for the spring? Since work equals force times distance, can I do force equals work divided by distance and do 50 joules over 0.08 meters? How's that? Does that work?
No, because the amount of force needed increases, the length gets longer.
Okay, we have one vote for no. The rest of you agree with that? So what does this assume? This assumes that this force, whatever this force is, 50 over 0.08, is a constant force to stretch it this far. And we know that's not true. So he's right. This doesn't work. The force changes as you stretch it. Just taking W divided by D would assume a constant force to get it to stretch to that length. And that's not true. It can be an increasing force. So we know that work accumulation is modeled by this. So our 50 joules is an amount of work. And that for some displacement. So really, this information tells us that 50 equals the integral from 0 to 0.08 kt dt. So the missing element here is, what is k? What is k? Once we have the spring constant, then we can find accumulated work for all different kinds of situations stretching the spring. All right, so we need to solve for k. Let's do it. What is k? We're gonna divide both sides by integral of 0.08. Divide both sides by dt. Is that gonna work?
Would you use force is equal to k times x?
Except that we don't know the force. Yes, that would work. Force equals kx, and x is 0.08, but we don't know the force to hold it there. If we knew the force to hold it there, then k would be a cinch. F divided by x. What we know is all the work it took to get it there. And that meant the force was varying along the way. So without this force, without knowing that, we're stuck with this expression to figure out what k is. And what's the big obstacle with this expression?
There's an integral that we have to get rid of.
Yeah, and what's that? What do we call that?
What would you just take the derivative of?
Open form, right? Open form is our obstacle here. Open form would make it, for our purposes right now, what we know, it's impossible to find k. There's no simple algebraic divide both sides by this. Take the log of both sides. There's no simple algebraic process to get this k unstuck out of this integral. So open form, for what we've done so far in the course, open form is an obstacle here that's preventing us from solving for k. Okay, so what we're gonna transition to in the course is, given an open form net accumulation function, we want an equivalent closed form. Closed forms are easy to solve algebraically. They give us rapid fire results like we've talked about. And so that's what we're going to focus now in the course is given an open form net accumulation function or integral accumulation function, being able to get the closed form equivalent. Okay, so that's where we're going. So we have to put this problem on hold. Okay, we got to work on that, which I just talked about, figuring out what a closed form would be for this. And once we have a closed form for this expression, then solving for k would be just based on algebra. Does it make sense? Okay, so we're gonna put that problem on hold, and then we're gonna talk about how are we gonna get closed forms from open form. Okay, so let's start with that's the net accumulation of a quantity given by the function f starting from x equals a. So I've got some quantity and I want to express a net accumulation starting from x equals a. What do I need? If the quantity is given by function f, what do I need to express the net accumulation of the quantity f?
The rate of change of f.
The rate of change of f, and I'm going to set up what? Integral, right? Yeah. And here's this integral we've been working with all semester. We need the rate of change of whatever that quantity is. We're going to do the integral from a to x of the rate of change t dt. Okay? So how about the total accumulation? What do we need to get? This is the net accumulation starting from a. What else do we need to have this function be the total accumulation?
Initial.
Yep, and we express that as f of a, right? So f of a would be like all the accumulation before a, like from negative infinity up to a as a lump sum. And then starting from a, we have the net accumulation that we're accumulating bit by bit, right? Accumulating bit by bit. So what I want to do here is I want to subtract f of a from both sides. And when I subtract f of a from both sides, I'm back to my net accumulation function right over here, right? And that means that this side also equals the net accumulation. But now they're expressing that net accumulation in two different ways. This one's is expressing it as final value of the quantity minus the initial value of the quantity. This one's expressing it as the accumulation of many small bits of change. But they're both the exact net accumulation of our quantity f starting from a, starting from x equals a. I'm going to change the order here and see if that looks familiar to you from Calc 1. Do you recognize that?
Isn't that like definition of an EF?
Yeah, so this is the equation that's representing the fundamental theorem of calculus. So the fundamental theorem of calculus, what does it do? It expresses the exact net accumulation of a quantity at that rate in two different ways. It expresses it here in an open form, and that open form is reflecting the process of a running total of bits of change, right? Like we're summing up bits of change. And then it also says that net accumulation is the same as final value of the quantity minus the initial value of the quantity. And this is going to be our key to writing closed form, is to rewrite a net accumulation function in this form. So we're going to use the fundamental theorem of calculus to write open form expressions in closed form. Okay, so, and we talked about closed form. Closed forms is built from common familiar functions that are just highly efficient for computing, right? Lots of results quickly. We can do algebra on those very easily, okay? Whereas we can't with this. So how do we get, so we've got the rate function, how do we get the function f from the rate function? So let's talk about the other way first. How do we get the rate of change from f?
Derivative.
Yeah, the rate of change of a function is the derivative, right? But for our purposes, we're going to have the rate of change. We're going to need to recover the original function in order to use this form for closed form. So what will it take given the rate of change and we want to recover the original function? That will be a matter of
Antiderivative.
Antiderivative. So there's two key components to writing open form expressions, net accumulation expressions, in a closed form. The first is the fundamental theorem of calculus, that we're rewriting this net accumulation of changes as final minus initial. That's the first thing, fundamental theorem. And the second key to this is we're going to need the antiderivative of that rate function. And that's what's going to form this function for our closed form. So fundamental theorem of calculus, antiderivative, put those together. Those are the two ingredients for writing open form net accumulation functions in closed form. And this will be the structure of our closed form. All right, so let's practice here. Just some easy ones. So I'm going to give you some expressions here, and for each of these, we're going to explain the meaning of the expression, including all the details, all the specifics. Then we're going to write a computable expression that gives the value exactly. And what am I talking about there in part B? What is that really talking about?
The exact net accumulation.
Okay, but this is exact. Yeah, so this is talking a computable expression that gives the value exactly is really talking about closed form. And then we're going to solve or simplify that closed form expression if appropriate. Okay. So before we start, there's one little a notational thing here. So we saw this is the fundamental theorem. There's an intermediate step that's often helpful with this, and that is, find once you find the antiderivative, don't go right to this structure. Write down the antiderivative in terms of t, and then holding on to the a and the x, right? So then you put a vertical bar, ax, which means this. It means we're going to plug in x, and we're going to plug in a, and we're going to subtract. Okay, so this is just, instead of trying to do two things at once, it's nice let's focus on the antiderivative and write that down, and then use this notation to mean, okay, now in the next step, we're going to plug in x, we're going to plug in a and subtract, okay? So here we go. So what's the meaning of this expression? What does this mean? Any volunteers?
So in this expression, cosine of u du, that would have been like your m dx.
Okay.
It's like your rate of change. And they want to find the accumulation from -1/2 to some value x.
Okay. Okay, very good. This is the net accumulation from -1/2 to any value x. If the rate of change is, so just one thing, what is the rate of change? Is it cosine x dx?
Cosine u.
Yeah, cosine x, right? So we're just using u. U is a placeholder for x value, right? So the rate of change is cosine x, and we want the net accumulation from -1/2 to x. Okay, so what do we need first? We need antiderivative. So here's the thing, in the next week or couple weeks, we're going to be working on antiderivatives. We don't want to learn a whole new set of rules to find antiderivatives. What we want to do is we want to just know our derivative rules so well that we can do them backwards. That's the way we want to think about antiderivative. Not learning a whole new set of rules, but knowing the derivative rules well enough to do them backwards in our head. So what we're asking is, what function has the derivative cosine x or cosine u? Right? What function, if we took the derivative of it, would we get cosine u?
sine.
Many of you are saying sine. So many of you are saying, and that's right. So it's sine. So we're going to start by writing sine of u, as that's the antiderivative of cosine, because the derivative of sine is cosine. And then we'll use this notation here, which means that. And now we're ready to write the closed form, which is sine of x minus, so final value of the quantity, minus initial value of the quantity. So what's the meaning of this expression? What does this function give us? What's the meaning of this expression, or what does it give us?
The exact net accumulation in closed form.
The exact, so the point is, it gives the exact same thing this does. It's the same function. It's just in a different form, closed form. It's the exact net accumulation of a quantity whose rate of change is cosine x, starting from -1/2, accumulating to x. So it's the same thing, but just now in a computable form. Okay, does it make sense? So we've just written our first closed form expression given an open form expression, right? We've been plugging these into GC and letting GC give us, using function notation, letting GC give us the results. Now we have a closed form equivalent of this open form expression. And we wouldn't really need GC anymore, right? Next one. So what is this? This is the net accumulation of a function whose rate of change is 3e to the x, starting from 0, accumulating to x. First thing we ask is, this is our rate of change. The function we need has a rate of change of 3e to the x, or 3e to the w. What function's rate of change is 3e to the w?
3, like 1, so.
3e to the w. Remember this? So remember that this was the special function, exponential functions. They have their own derivative, right? So the derivative of 3e to the w is 3e to the w. And so then the antiderivative is 3e to the w. Okay? We're going to do that from 0 to x. And so then we have plug in x, plug in 0, and subtract. Now, is this 3e to the x minus 0?
No, it's 3.
3. Just because one of your limits of integration is 0 doesn't mean that the expression will be evaluated at 0. So this is a really common mistake the students make. They see the 0 and then they just say that's the 0. Whatever you get when you plug 0 in must be 0. Well, there's lots of examples of functions that if you plug 0 into, it's not equal to 0. Okay? You've got to plug it in and work it out. Okay? So, and that there's a question on the exam where this comes into play, and it's about 10 to 20% success rate with students, and kind of the underlying reason that students miss it is because they assume plugging 0 in just doesn't give 0 for this. Here's a perfect example where it doesn't. Plugging in 0 here gives 3. Questions on that one? Okay, how about this? So, again, we have the net accumulation of changes in a quantity whose rate of change is x to the 4th, starting from 1, accumulating to x. So we need a function whose rate is t to the 4th, so, or derivative. So remember the power rule. Power rule for derivatives, you reduce the power by 1. So here we're going to raise the power by 1, right? So if you do antiderivative, like the derivative of t to the 5th is going to be something to the 4th. So the power rule for derivatives means reduce the power by 1, so antiderivative, we're going to gain the power. So is this correct? Antiderivative?
It's a 5 by 5.
Yeah, so here's this is a really important technique we're going to use. You get something close, you get something, in the ballpark, take the derivative of it and see if it's exactly the rate function that you started with. And if it's not, make an adjustment. So what's the derivative of t to the fifth?
5t to the fourth.
5t to the fourth. We don't have a 5 here. So what adjustment can we make so that when we take the derivative, there won't be a 5? 1/5, or divide by 5. So now that function's derivative is t to the fourth. 5 times 1/5 is 1, t to the fourth. And we're going to do from 1 to x. So now we're going to do final minus initial. We've got the quantity function, and net accumulation means final value of the quantity minus initial value of the quantity. What's the meaning of this expression? What's the meaning of this expression?
It's the closed form of the integral that we started with.
Okay, so the meaning of it is not that it's closed form. So closed form is the form of it. But what does this function give, or what does it do? Good. The net accumulation from 1 to x when the rate of change is x to the fourth. That's right. It's the net accumulation of a quantity starting from 1 up to x when the rate of change is x to the fourth. Okay. If you have a question, just jump in and ask. Okay, so here's a little more challenging one. We got to really think about what's happening here. So 2a times the square root of a squared plus 3 is our rate function. So we think about, okay, what function, if I took the derivative of it, would give me something that looks like this? And if you remember by the chain rule, remember the chain rule? Where you multiply by the derivative of the inside? Do you see that this is the derivative of the interior function? So you say, oh, this is like a chain rule derivative. So what function, if I took the derivative of it, would give me this? So if I do antiderivative, this thing will go away. It'll collapse back inside. I won't have this anymore for antiderivative because it's in the derivative that we chain it on. So it's going to go away in antiderivative. So we're going to have a squared plus 3 to what power? 3 halves. We're going to raise the power by 1 just like we did in this one. But then there's a 3 halves that we're going to end up having if we took the derivative that we don't have here. So we need 2/3, right? So 3 halves times 2/3 is 1. A squared plus 3 to the 1/2, there it is. Times the derivative of the inside, 2a, there it is. Okay, so we're going to practice lots of that. But the point is, you can recognize that, oh, this was the result of the chain rule. If I go backwards from the chain rule, this is going to go away, right? And then I'm just going to raise power on this part. And that from 10 to x. So we have 2/3 x squared plus 3 to the 3 halves minus 2/3 times 103 to the 3 halves. So here's my net accumulation function starting from 10 if this is the rate of change. But now it's in closed form. Yeah.
Is it written as 10 to the third? What happened to the 3?
10 squared plus 3. I just did the math. 10 squared plus 3 is 103, right?
Oh, okay, it was 103. Okay, I was like, wait a second.
Okay, real quick, just one more example here. An easier one. Oh, need to erase some more. Okay, here's one. 0 to 0.8 of kx dx. Look familiar? This was our this is our open form. We were trying to get x, right? We were trying to get x, and we were stuck. Now we can do it. What's the antiderivative of kx? So it's going to be
2x squared.
It's going to be power rule. We're going to raise the power on the x to 2, but then we're going to need a 1/2. Okay, so that's going to be k times 0.08 squared over 2. And we saw that equaled 50. And so now we have unlocked the open form, and now we can easily solve for k, right? So in the spring example, we said the accomplished work was 50 to stretch the spring, 0.08. Now we have a closed form of that expression, which makes it easy to solve for k. And that gives the spring constant, and then we can answer that any question now about the spring that they give us. Okay.
Sorry, where did the 50 come from?
That was the problem. The problem said it takes 50 joules of work. Back at the beginning of the lecture, it takes 50 joules of work to stretch the spring this far.
Oh, so that k times 0.08 squared over 2 is equal to 50.
Yeah, exactly.
Okay.
So this was this is the closed form of that work expression. And since that's equal to the work, it's equal to 50, allows us to solve for k. Okay,